Hi, everyone. Thanks for coming. I'm really excited today to talk to you about how to make your PySpark Data Fly using Apache Arrow and introducing the new Arrow Flight framework. So first, just a little bit about myself. I'm a software engineer at IBM, and I work at the Center for Open Source Data and AI Technologies, or we call it CODA for short. I'm a committer for Apache Spark and Apache Arrow, and also a maintainer for Tensorflow IO, which I'll go into a little bit later. A little bit about CODA. We aim to make AI solutions dramatically easier to create, deploy, and manage in the enterprise. And obviously, open source plays a big part in that, which is why I get to work on cool projects like Spark, Arrow, and TensorFlow. So the topics we're going to cover today, I'll begin by going over a brief intro to Apache Arrow, in case you're not quite sure what it is or you've never heard it before. And I'll go into introducing the new Arrow Flight framework, which has been around for the past couple versions of Apache Arrow. And I'll talk about what it means to be able to speak Arrow, so a system can take advantage of using this new flight framework. And I'll end it by going over an example of how to transfer data from Spark to TensorFlow using the Arrow flight framework. So what is Arrow? Well, Arrow is a standard format for in-memory columnar data. So the format itself is language agnostic, but there exist implementations in many different languages, including key languages like Java, C++, and Python, and also lots more growing. So there's also Rust implementation, JavaScript, R, and more coming down the line. So Arrow itself is designed that the memory can be very efficient for analytic operations on modern hardware. That means the layout's designed so it's optimized for things like SIMD operations or doing massively parallel operations. Arrow is not a file format, so while you can write Arrow data to disk, it's not really suggested for long-term storage. There's other options for that, things like Parquet or Orc that are also columnar-based. And Arrow has built-in converters that can easily transfer data to and from those file formats already. So it's not really meant for long-term storage. Now, Arrow has built-in capabilities to work with Arrow data memory efficiently. You can zero-copy data within a process, take zero-copy slices, for instance. And there's primitives for inter-process communication built in. And kind of the primary data structure for that is what they call an Arrow record batch, which is a number of columns that each have equal lengths. And so it's a batch size. Now, why would you want to use Arrow? Because it's a common standard, that means it can be used by different systems that all take in the same kind of memory. And you don't need to end up writing a lot of special kind of converters or serializers and support every kind of file format under the sun for your application. So this leads to better interoperability between systems and makes life easier for us all. Now, the great thing about Arrow is that it's already been used by lots of different places and projects. This is an excerpt from a blog from the Apache website, and they highlight the different new technologies that Arrow has been that have been taking advantage of Arrow, and the amazing momentum that it's had over the past 3 years since it's been a top-level project. So you can see a lot of projects such as Spark, NVIDIA, Rapids, Pandas are already using it and have Arrow, the ability to understand Arrow already. So let's move on now to talk about what the Arrow Flight framework is all about. So Arrow Flight is an Arrow native RPC framework. And it defines a standard protocol to transfer messages around that contain Arrow data. So while the core of Arrow provides basics for inter-process communication, the big data systems that we use today are a lot more complex and really require something more in order to fully exchange their data. So this is where Arrow Flight comes in, and it makes it easy to efficiently move this data around the network. And it kind of builds upon Arrow and introduces 3 new concepts. The first is Arrow data as a service. Second is batching streams together, and also stream management. And we're going to go into each one of these in a bit more in detail. So what does it mean to make Arrow data as a service? Well, the framework provides an extendable data service, and it's centered around clients performing actions that involve either producing or consuming Arrow data. So a client could get or put Arrow data into the service. They have the ability to list what kind of actions are available, and also you can extend it to provide your own custom actions. You can kind of think of it as like an ODBC driver for in-memory data. So stream batching is the concept of combining multiple Arrow streams together. Now, I mentioned before the Arrow record batch was a primary data structure for inter-process communication. And an Arrow stream is basically just a schema followed by a sequence of record batches. So if you haven't had enough terminology thrown at you already, there's one more, and it's kind of important, but we're going to define a flight as being composed of multiple Arrow streams. So these different streams can come together from different endpoints, and it's built to transfer data in batches, and make sure things are transferred efficiently. And each endpoint has a location info where you can use to take advantage of data locality. So here's just an example of a flight, and there's 2 streams in it, and each stream has 2 record batches. So you can think of the flight as like your entire data set that might span over the network. So Arrow Flight provides the ability to manage these different streams within the framework. Flight info is a list of endpoints that contain locations for each stream within that flight. And each stream is referenced by a ticket. So a ticket is an opaque structure that makes sure it's unique for each stream. So you can think of your flight info as like your itinerary that you would get from an airline, and you get maybe a series of tickets that you use to eventually get where you need to go, and in this case, you would want to consume all the data in your flight. So now your service can handle more than one flight, and it differentiates between flights by using a flight descriptor. And with that flight descriptor, you can define how your flight is composed. You can do things like set a batch size or even make a SQL query. So let's take a look at the flight descriptor. It comes in 2 different flavors. The first is just a simple string-like path that you would probably use to reference a particular data set. The second is an arbitrary command where you might be able to use something like a custom protocol buffer message. So here we have one that the client would provide a SQL query and a number of batches, a number of records they want for each batch in the streams. You would then define your ticket to probably have a reference to this descriptor and make sure that it is unique for each stream. Let's go over what the ticket sequence and exchange looks like for a client that wants to consume the entire flight. So the client would begin by messaging the flight service to get a flight info, passing in the descriptor of what flight it wants. And it would get back this flight info, which contains a list of endpoints with tickets for the streams. Next, it would get a stream by passing in a ticket. And once it has that stream, it can begin iterating over the Arrow record batches, getting one after another. And once it gets one, the idea is to process it and then move on to the next one. So what are the benefits of using this Arrow flight framework? Well, applications can make use of the client interface and exchange this data as a standard format of record batches. So that really abstracts a lot of complexity away from your application, and you really just have to implement this client interface and use this standard format of data exchange. A lot of the complex communication that goes around in the framework is handled internally by the flight framework. And it ensures that you send data around efficiently and data is batched up and making minimum copies as possible. By also using a standardized protocol, we can ensure that there's things like authentication right out of the box, so you can make use of that. You're also able to define and support different kinds of transports over the network as well. And it can handle back pressure. So the current status, there's some good news and bad news. The good, there's a common protocol already defined and using protocol buffers. There are prototype implementations that exist in Java and C++, Python. But bad news, it's still a little bit experimental and it's being refined. But there's a lot of work going on right now in order to harden this and make it ready for production. So it's not quite there yet, but it's still useful to try out right now. So I want to cover what it means to talk Arrow. So if you have a system that wants to make use of this framework, what does it need to do? At the very minimum, this system will need to be able to produce or consume an Arrow stream. And a stream, once again, is a schema followed by record batches. So Spark kind of does that already. There's a lot of work that went in to use Arrow to communicate from the JVM to the Python process. And there's Arrow converters built in that convert Spark internal data to an Arrow format. But all these APIs are currently internal and not public. So there's a couple Spark JIRAs that exist that seek to change that and expose Spark data as Arrow. You can check those out right now. So using these converters already, we can kind of hack Spark up a little bit and build a flight connector that's suitable for testing. Now TensorFlow, on the other hand, can already talk Arrow. There exists a package Tensorflow IO, which has Arrow datasets already built in. And Tensorflow IO is a subrepository of TensorFlow that's maintained by the SIG.io community. In addition to the Arrow datasets, there's also a lot more inputs. The package contains a lot of different datasets to support inputs and file systems. So there's lots of different stuff there. A lot of things that used to be in the legacy contrib folder of TensorFlow ended up moving here, and there's been a lot more added. It's easy pip install, and so I definitely urge you to check it out. I'm sure you will definitely find something useful there. For our example purpose, we're going to make use of the Arrow stream dataset that exists in there. All right, let's jump into using an example with Arrow Flight, and we will send data from our PySpark client to TensorFlow, And hopefully some of these topics that we covered will be a little bit more clearer. Now this is just meant to show you how things get connected up and the data is exchanged. It's probably not something that you would want to be doing in production. So we'll begin by defining our service. We're going to be using a simple in-memory data store to store our Arrow data. And when a client puts data into the service, it's basically just stored as a hash map using the flight descriptor as a string ID to use as a key for the stream. This service is actually built into the Arrow flight examples that exist if you were to download it today. So it's just pretty basic, but it's going to serve our purposes for this example just fine. All right, let's go on and define what our clients are going to be. We're going to have a PySpark client. And we're going to use an existing data frame and put that data into the service. And this is basically just going to be a map operation where we convert a partition into Arrow format as a stream and then send that stream onto the service. So a ticket in this case is roughly equivalent to a partition index. Now for TensorFlow, we're going to use the Arrow stream data set as we talked about. But we need to write a little adapter that will enable us to get the flight info from the service and pass through each stream that it receives back into the Arrow, into the TensorFlow data set. So it's going to end up requesting the whole flight, and it gets one batch at a time that it processes. And the data set operation is going to output tensors. So let me just go over how the data kind of flows in this example. We can see we have a Spark worker here, and it has, looks like 2 partitions. Okay, and so one task of the partition, so the worker is going to run a task and basically tell the service, hey, here's some of my rad Spark data, and the service accepts it. And then another task will come along and say, here's a little bit more of my rad Spark data. Now the flight service is going to accept all that data and classify it under the rad Spark data descriptor. Now the TensorFlow client will come along and say, hey, I'm interested in all this rad Spark data you have. Tell me how to get it. So it gets this flight info back that has a list of endpoints and tickets, 2 tickets, 1 for each of these streams. So it gets the first stream and starts requesting Arrow record batches, and will iterate through all 4 record batches while it's processing. So here's what the code kind of looks like from our hacked up clients. Since these aren't official clients, it's kind of hard to tell what the exact APIs might look like. But I think it's pretty close to how it might be eventually. So let's take a look at what we have here. So at the top is our PySpark client. And what we need to feed into our connector is an existing data frame. Now, obviously, for this example, you would want to make sure your data frame has small enough data that you're not going to overload your service. So we give it an existing data frame, and it will basically perform that map operation, converting Arrow data into streams and sending it to the service. We also need to give it the IP address so it can, of the service so it can connect to it. And we want to tell it the descriptor for what kind of data we're using. So we're giving it this rad Spark data. Now on the TensorFlow side, we define our data set, and we kind of do the same thing. We need to give it an IP address for the service to connect to, and we tell it what, give it a data descriptor to tell it what data we're interested in. And because it's a TensorFlow ob, we need to define the shape of our data, and we can use our existing schema from our Spark data frame to do that. So that's what this last argument does. So once we put that into a session and run it, our iterator will connect to the service and begin requesting Arrow record batches, where it can then iterate over and output data as a tensor. So an important thing to note here is that we're using a Python interface for both of these systems, but in either case, the actual data doesn't reside in Python. So for Spark, it's storing data as internal rows. And for TensorFlow, Spark is storing the data in the JVM. TensorFlow, on the other hand, is defined, the C++ kernels actually do the data processing. So we have to get data into C++ and in a tensor format. So using Arrow as a common medium, we're able to exchange this data completely in memory from the Spark JVM all the way to the flight service and back to the TensorFlow C++ client. And throughout this whole process, the data never needs to go through Python at all. Now, I love Python, and it's great, but if I don't need to send my data through pickle format, that's just fine. So any time this would have to go through Python, it would just be more added overhead. OK, let me just do a quick recap on what we covered today. I went through an overview of Arrow. If you don't already use it, I urge you to. It will make your life easier and more fulfilling, not guaranteed. I went over the Arrow flight framework, which is kind of a new thing that's being introduced in the latest Arrow versions. And this allows you to efficiently move your data around the network. And there's 3 main points that you want to cover with that. The first is using Arrow data as a service, which allows us to provide a producer-consumer relationship between Arrow data. The idea of stream batching, which is taking this Arrow stream and being able to define a flight, which represents our data all over the network. And the idea to manage these streams by providing things like a flight inflow that describe our data and a ticket system to request whatever data we're interested in. And finally, I went through this simple example to show you how to things get connected up. I have the the code for that if you wish to kind of go through it. I'll have a link in the next slide. And that's about all I have. So here are these links and references. There's the flight specification that you can check out. It's defined as in the Aeroflight protocol file. And I urge you to check out TensorFlow IO. Like I said, it's pip installable right now, and there's lots of other different data sets that are available for you to try out. Some of the related Spark JIRAs that cover exporting data from Spark as Arrow format, And the code we went over is available at my GitHub repository. Feel free to check out. So that's all I have. Welcome to take any questions.
Thank you. Anybody has got any questions? There is a mic here. You can come here and ask questions.
All right. Well, thanks very much, everybody. Huh?
I was about to go for the microphone.
Oh, they cut you off.
Hey, Brian, just a few questions here.
Okay.
Just to clearly understand Arrow in the Spark context, if I want to describe a pipeline that has the minimum amount of serialization and deserialization, say we are bringing data in a raw data format, might be in JSON. Normally, I would take that, and once I get it into Spark, I would process it and save it down to Parquet to disk. So first of all, I understand that when I save it to Parquet to disk, Arrow's not involved in that process. Okay. So then when you bring it up, so it's really that it doesn't help you to know that you're going to be using that the next step is Arrow. When you save it down to Parquet, it's just simply Parquet and there's no...
So saving to Parquet, yeah, Arrow's not involved in that at all. Loading Parquet files, Spark will actually load that as a columnar batch, which is the Spark internal structure. So at that point, it knows that it's using columnar format, right? And so ideally, yes, you could load that into Arrow format right off the bat. And then, so Arrow's being used in other ways like Pandas, UDFs. So you could then keep your columnar format, perform all these columnar operations, and then go on to export data in columnar. And so all along the line, keeping that in columnar format. That would be possible. And one of the JIRAs that I referenced here, that's kind of part of it, is enhancing the columnar data support. So definitely, hopefully, we'll get to that in the future. Yeah.
Okay, great. And you said that would be possible. That's preferable also, right?
Yeah. So I think kind of the driving force between one of the JIRAs is that to be able to accelerate some of the columnar processing with the GPU. So that does have some benefit. You know, we'll have to see how much that provides, but you know, keeping things columnar does have its advantages, but then if you need to convert it back to do row processing, there's overhead there as well. So there's going to be trade-offs, yeah.
You described about the endpoints that so you can have multiple streams with multiple endpoints, but the endpoints, can there be a list of endpoints, or is there some HA availability in there, or is it essentially just a single, if it's down, and you can't access it?
Sorry, I couldn't hear the last part.
I have a question about the endpoints. So you mentioned that you can have multiple streams all with their own endpoint, but are the endpoints HA, or are they essentially a single host? If it's down, you cannot access that particular stream at that particular time, or is there maybe a list of endpoints, or how does that work?
So I'm not entirely sure if. So you're talking about like, would the data physically be attached at these different endpoints? I think it is possible for the client to connect, make a separate connection to each one of these endpoints and get data separately. Is that kind of what you're getting at?
What if the endpoint is down? Is there a way to still get your data from one of the other endpoints potentially, or how is that designed?
Oh, okay. You're talking about like high availability. Okay. Yeah, I don't think any of that's built into the framework. It doesn't go into that kind of depth. When you're defining your own service, you could definitely go along that route, I think, but that would be more of, it's not automatically done by the service. It's something you'd have to write on top to enable that, but it would be possible, I think.
There's no, is there support to provide a list of endpoints potentially? So if one is down, you could go to another one in the definition, or, yeah?
Yeah, I think so. I mean, the service provides a list of endpoints. You could definitely have your data duplicated around the network and have your service kind of filter that through, find out which is the best endpoint for the client, and send that through. Yeah, that's probably work done as defined in your service.
Okay, thanks.
This winds up being probably a related question. Can you compare and contrast Flight to just writing Arrow buffers into Kafka?
I'm not too familiar with Kafka, but I know it has maybe some kind of limitations to the message size. So the good thing about the Flight framework, and I think why they wanted to write their own, is they can ensure that the service, when reading data over the wire, can be done with like a zero copy. So just the idea that we're going to make this data transfer as efficient as possible. It's for working with Arrow data, so we'll completely optimize it for that.
Okay, thanks. Any other questions? Perfect, thank you.
Thanks.